Welcome to The Explainer, where we break down big ideas. Today, we are diving headfirst into one of the biggest ideas of them all, parallel universes. And we're going to see why this might be less science fiction and a lot more solid science than you probably think.
Okay, so let's jump right in with that famous question. You've probably heard of it, but we're not going to treat it as just some weird philosophical brain teaser. We're going to treat it as a genuine scientific puzzle that, when you really dig into it, points to a profound and kind of shocking truth about the nature of our reality. To really solve the riddle of the cat, we first have to back up a little and understand the central mystery that lies at the very heart of quantum mechanics itself. See, physics kind of has a split personality. On one hand, you have the classical world of Isaac Newton, the world of baseballs and planets. Everything is predictable. If I know where something is and where it's going, I can tell you its entire future, guaranteed. But then there's the quantum world, and down there, things are described by something called a wave function. And this wave function also evolves predictably following the famous Schrödinger equation, spreading out smoothly, almost like a ripple in a pond. But here's the problem, the big puzzle. We never actually see this beautiful, elegant, spreading wave. Whenever we go to look, whenever we make a measurement, we always find the particle in just one single definite spot. Poof, the wave is gone. So, to try and bridge this gap between the spreading wave and the single point, a physicist named Max Born just added a rule. It was almost like a footnote to the theory. He said that the wave doesn't tell you where the particle is, it just tells you the probability of where you'll find it. And just like that, randomness was injected into the very heart of physics, which made a lot of people, especially Albert Einstein, deeply, deeply uncomfortable. Now, this whole idea of having two different sets of rules, one smooth, wavy rule for when you're not looking, and another random, jumpy rule for when you are looking, it just seemed plain wrong to the physicist Erwin Schrödinger. He thought it was ridiculous. So he designed a famous thought experiment just to show everybody how absurd it really was.
And this is where it gets really clever. You see how each step in this chain reaction links a tiny, invisible quantum event, the decay of a single atom, to a huge, real-world outcome? The fate of the atom and the fate of the cat become completely and totally intertwined. They become, in the language of physics, entangled. Because according to the rules of quantum mechanics, until you actually make a measurement, that atom isn't one or the other. It's not decayed or not decayed. It exists in a bizarre combination of both states at the exact same time. It's in a superposition. And because the cat's fate is now entangled with the atoms, well, you see where this is going. It means that before you open that box, the cat, too, is in a superposition of being both alive and dead. And this was Schrödinger's big gotcha moment. He was basically screaming, see, this is obviously absurd. A cat can't be alive and dead. So to solve this, let's play detective. Let's investigate the three key components of this whole experiment: superposition, entanglement, and the act of measurement itself. One of these has to be the weak link. One of them has to be where our understanding is going wrong, right? So, first up on the chopping block is superposition. Now, it sounds completely impossible, I get it, but here's the thing. We have absolute, rock-solid proof that it's real. The classic evidence is the famous double-slit experiment. You can fire a single electron at a barrier with two slits in it, and somehow it acts like a wave and goes through both slits at the same time to create an interference pattern on the other side. This isn't just a theory. We can do this in a lab. So, superposition, our first suspect, it's on solid ground. It checks out. All right, next on our list, entanglement. This is the phenomenon that Einstein famously and skeptically called spooky action at a distance. It's what happens when particles interact and their fates become linked no matter how far apart they fly. And the reason this isn't some spooky, faster-than-light communication is actually the key to understanding it. The two particles aren't really two separate things anymore. They are two parts of a single unified system, described by one wave function. So when you measure one particle, you're really just getting information about the whole system. And just like superposition, entanglement has been verified experimentally over and over again, so it's solid too. So, if superposition is real and entanglement is real, that leaves us with only one suspect left standing, the act of measurement. Why on earth should the entire universe operate by a completely different rule just because we look at it? I mean, what even is a measurement, really? It's just another physical interaction. It's just more quantum systems bumping into each other. This puzzle, this problem of measurement, leads us to a truly radical, but in many ways, incredibly simple solution. What if we just throw out that special measurement rule altogether? What if the wave function never actually collapses? This is the core idea first proposed by a brilliant physicist named Hugh Everett. In this view, when you open the box to check on the cat, you don't force reality to make a choice. No, you simply become part of the quantum system yourself. You get entangled with the whole setup. And what that means is the universe branches. Reality itself splits in two. A version of you becomes entangled with the state where the atom didn't decay, and in that world, you see a living cat. At the exact same moment, another version of you becomes entangled with the state where the atom did decay, and in that world, you see a dead cat. Both outcomes happen. They just happen in their own complete, parallel, and totally non-interacting realities.
Okay, I know. That sounds completely wild. It sounds like something straight out of a comic book. So let's try and address some of the most common objections people have by turning to an expert, Caltech physicist Sean Carroll. The first big question you always hear is this. Wait a minute. If you're creating whole new universes every time a quantum event happens, where does all the extra energy and matter come from? Isn't that a violation of the laws of physics?
Well, the answer is that you're not actually creating new energy from nothing. The better way to think about it is that the total energy of the overall wave function, the whole multiverse, is always conserved. It's just being partitioned or sliced up among all the different branches as they split.
Okay, what about this one? Does the many worlds idea mean that anything I can possibly imagine is happening in some other universe? Is there a universe where I can fly? Not at all. The universe is still governed by the strict laws of physics. The wave function still has to obey the math. An electron is never just going to randomly turn into a proton because that's not allowed by the rules. But for any outcome that has a non-zero probability according to the math, no matter how tiny that probability is, well, then yes. A version of you becoming president, the chain of events might be incredibly unlikely, but it's not impossible. So that world does exist, somewhere out there in the multiverse. So when you pull it all together, this really leaves us with two very different ways to view our universe. On one side, you have the traditional Copenhagen interpretation. This is what most of us were taught in school. It says the wave function is just a tool for calculating probabilities, and that there's this special, mysterious process called collapse that happens when we measure things. On the other side, you have many worlds. And yes, it seems extravagant with all those parallel universes, but from a mathematical standpoint, it's actually much cleaner, much more elegant. It just has one rule, the Schrödinger equation. It simply takes the math we already know is true and follows it to its logical conclusion. And the implication of that is just profound. It suggests that the founders of quantum theory might have had it exactly backwards. That spreading wave of possibilities isn't just a calculational tool. It is reality. The whole thing. And our personal experience, our perception of a single solid outcome, is just our limited view from inside one tiny sliver of that vastly larger branching multiverse. So let me leave you with a final thought to chew on. Every single tiny quantum event in your body, happening thousands of times a second, could be splitting your reality into countless new branches, which means there are countless other versions of you who took different paths, made different choices. So the question is, what specific chain of choices, what specific series of chances led this version of you to be right here in this moment?